Good afternoon and a very warm welcome to all. Myself, Assistant Professor Harsh Sharma. Understanding the importance, scope, and relevance of digital architecture from our previous sessions and based on your feedback, we at APID are trying to work upon conducting a workshop and a certificate course on digital and parametric architecture. Hence, as a part of that proposal, we have dedicated today's webinar as an orientation session towards understanding computational design, tools, software and methods, scope, benefit, application, actual project and research work, and finally the format of proposed workshop. We have with us two guest speakers today for today's session. Our first guest speaker, Drishti Korat, an alumni of APID, is an architect and an interior designer with a keen inclination to integrate computation technology with design. After graduating from CEPT University with a specialization in computational design, she established Studio Dwandvo with the aim of exploring parametric design approach in the fields of interior, architecture, and landscape. She retains a connection with academics by conducting workshops and studios that focus on algorithmic thinking. Our second guest speaker, Parul Chauhan, again an architect with undergraduate study from DIT Dehradun, Masters of Design in Computational Design from CEPT University. She has been involved in developing parametric design studios at Sharda University at undergraduate level and is a visiting faculty at Delhi Technical Campus. She is the founder of PA Workshops and actively runs workshop on material system and parametric software in various design and architecture universities in the northern region. We very warmly welcome both of you. Before we begin the session, a small request to all the participants to be very attentive and responsive throughout the session, as this would help you to make an informed choice regarding your enrollment into the proposed upcoming workshop. And also kindly put up all your queries in the chat box. We would discuss them at the end of the session. Thank you all. And now I welcome our guest speakers to continue with the session.
Thank you, Harsh. Am I audible?
Yes, very clear.
Yes. Thank you so much, Harsh, for that introduction. Good afternoon, everyone. I hope most of us have joined. Should we wait for a while or go ahead?
No, I think we can start.
Okay, super. Harsh, actually, I think this seems to be the fact that I'm on loudspeaker because I'm able to hear my own voice.
It could be because of that reason. If you can use your earphones, it would be better.
I'm already on my headphones.
So I'm not understanding why is it happening. Just a second.
Yeah. Also, there seems to be a lot of disturbance. Yeah, now it's gone. Okay. All right. So good afternoon. Today, my colleague Parul Chauhan.
Drishti, are you logged in from
Yeah.
two devices?
No.
It's just one device. Is it working well
Yeah.
now? Or...
Yeah. So I'm presenting my screen, right? So that's why it is showing two devices, but that's essentially my video and my screen. That's why you see two logged in.
So you are just logged in from your laptop.
Correct.
So is it still echoing?
No, now it's gone.
Okay, sure.
It's
So
it's
go.
it's recurring in the between, but I think when you switched off your microphone, I was not
Then,
able to hear the echo.
okay. So I'll just keep it switched off and I'll pitch in only as required. So yeah, you may
Yeah,
go ahead.
sure.
Thanks.
Yeah, super. Just let me know in case my voice kind of gets disconnected or
Sure.
there's some issue, because I would not be able to notice. All right.
Sure. I'll let you know. Yeah.
Thank you, Harsh. So good afternoon, everyone. It's great to have you here. Today, my colleague Paul Chauhan and I will be kind of introducing you to this niche or kind of a relatively young field in design. So I'm sure you would have heard of parametricism or computational design. So we've all seen these sort of dynamic facades and views and forms that our beloved architects like Zaha Hadid or Pierre Kingels or Heatherwick or so they kind of use these designs. And I used to always wonder when I was studying at APID that how do they achieve these forms, how do they execute it, how do they design them. So here we're today going to look at this new paradigm of design, which is sort of a combination, or say a marriage between two fields, that is design and computation, or software computing skills or software engineering. So it offers kind of a completely new method of designing that, that takes a shift from the traditional methods that we're used to. So so for that, it's kind of important to understand what is that shift. And today we'll be covering, or today we'll be introducing you to what all these domains are, what are these terminologies, and what they mean. Because sometimes, we hear them or we read about them, but they're very overlapping, and there's some understanding that we can achieve through that. And we'll also be looking at what are the different tools used for it, what are the methodologies by which such designs are kind of executed. And we'll also briefly touch upon what is the potential of this system or this method of designing, and end with a pedagogical breakdown of how to study these methods. So I hope to make, I hope this session is as interactive as possible. We're a lot of us here. So like Harsh mentioned, I'd love for you to drop any questions that you have on the chat, and we'll take it up in the end. And yeah, yeah, let's get on. So we all know Gaudi. We've all been kind of, fascinated by the kind of architecture. So even today, it is the kind of architecture that's considered path-breaking. So we all know his famous church in Barcelona, and it is one such project that has been going on since ages, and which still is going on. So he was the first person to sort of start with what we know of today as computational design. So he definitely did not have the luxury of technology that we have today. So he did not have computers back then, but his methodology was incredibly scientific in nature. So what I mean by that is, when we approach a regular project, so for example, when you have a brief, when you get a brief from your faculty, or when we design a project, we get a brief from client, and our approach to design is generally very deterministic in nature. By deterministic, I mean that, for example, you have to design an institute in a hot and dry climate. You'd probably think that, courtyards work well. And but then how do you decide what would be the dimension? Right. So, for example, you'd say it to be 5 by 10, but there's no real way to kind of decide what should be the ideal dimension. So whatever methodologies that we use as a part of our traditional design processes are based on intuition and experience. So for example, you would say that depending on the grid, structural grid of the space, or probably the terrain, you came to the decision of the dimension of a courtyard. But there's no really way to test if that courtyard is actually, performing, or is able to control light, is able to is able to give you the kind of ventilation that you want to achieve through it. So, so to say that whatever approaches we've been using so far are kind of a process that is driven by the final outcome. So you kind of envision that I want to have this curvilinear form, and I want to have a curved roof going across, and every single decision that you make from the start of the process till the final product is kind of oriented towards this final form that you want to achieve. So that's the kind of process of design that we use right now. But what computational design, or parametricism, which is the more famous terminology that we know of, offers is a shift in design or a shift in design thinking, where our approaches are highly scientific and data based. So, for example, if I were to go back to the same question, and if I say that there was a way to determine what should be the exact dimension of the courtyard, and there is a way to test how much sunlight it is giving, or how much sunlight it is letting in, how much space it is eliminating, and how much current draft or wind current that it is allowing to generate, there's an actual way to test it with numbers, with data, with solid proof. so that you can be sure that whatever design you are trying to achieve is performing in the way you envisioned. It is to make sure that your design decisions are actually performing. So that's the shift in design thinking or in approach that this particular system or process offers. So let's look at how Antonio Gaudi did it for Sagrada Familia. So here's this video. We all know of this famous building, and he used to conduct scientific experiments by hand, so by analogous methods. So if you can see here, uh, this was his model to generate all those spires and all those articulations that you see on the surface of church and even the insides of it. So here he used different threads. Some of them are interconnected, some of them are catenary structures which are kind of hanging from two different points. And what you see in the sacks in between are weights. So he used this flexible system of model to generate forms where each of the outline of the form was determined by the threads, and that thread or the shape of the thread was modified by the weight that was hanging from it. So further on, we're able to see, so for example, this was the process that he used this chain. He started putting weights at different points, and whatever shape that resulted into was inverted and used for his design. So it was used to design his final form of the arches. So we all know that since gravity is kind of the major factor that we use to determine if our structures are stable or not, he used this same influence or effect of gravity, which is a constant across the world, to derive his outputs. So his inputs were these flexible threads, and he used gravity, and he kind of used output, or he was able to find out different forms using this method. Apart from Gaudi, Fray Otto is another such famous architect who started using this system in in a more analogous way, which is through manual flexible models. He used soap bubbles to kind of derive his canopy. I don't know. He's someone who won Pritzker Prize, and I don't know if you guys are familiar with his work. But Gaudi and Fray Otto together were people who kind of started with this entire design approach or methodology to design buildings. What we know of now is super famous Zaha Hadid, and all of us have always been kind of amazed by the kind of architecture that she produces and her firm produces. So this here we have an example of the collaboration between Zaha Hadid Architects and ETH Switzerland. So both of them have kind of come together to design this pavilion, which sort of illustrates the methodology or the process. So this is more or less an illustration of her design methodology for most of her buildings. So for example, you can see here, it's called Knit Candla, and this was a pavilion. So here you can see they're trying to develop different forms and different variations in the curvature in the boundary, and then that form was kind of converted into a mesh or into a grid system, and then it was analyzed. So different variations, it was analyzed for stress, it was analyzed for structural stability. So all these gradation kind of tells you how they're analyzed, and they used kind of fabric and broke them down and made a structure, exoskeleton if you may, and pulled this fabric and tied it with this exoskeleton. And once they had this exoskeleton in place, they used ferrocement kind of a material and covered the entire fabric with that material. And here they're again trying to analyze where are the points where there is more stress. And here you can see a render of the final outcome, which shows what kind of spatial quality this was able to bring in. So, this is a complete innovation of methodology of the system, of the design system itself, but also its execution system. So the materials used or the way the fabrication is done is highly informed by technology. So a lot of advanced technology was used to bring in these systems and put them in place. So all the famous buildings that we know of, Zaha Hadid or say Bjarkingels, are and Thomas Heatherwick's, for example, Serpentine Pavilion or Seed Pavilion. So all of these different examples that seem very fascinating, have followed this similar kind of process of designs. So let's kind of have a look at what these different terminologies are that relate to this domain, and what are the scales, various scales in which they're used. Um, so when we look at these forms, for example, here on the left you have this parametric pavilion, or in the middle there this generative mesh-like structure, which is a model. So we're all familiar with tensile structures, and in the end there's this grid mesh that has kind of pinched together to kind of construct these forms, which are a major shift from what we see as traditional spaces. So computational design or algorithmic design, scripting, biomimicry, associative design, optimization, material exploration. These are all different words that are thrown at us in magazines or in workshops and seminars, or when we hear these architects talk. But let's look at them in more detail and understand what all these means, or what all these mean, and how do they relate to the final method. So computational design is a larger umbrella, or a larger field under which we have various subdivisions of parametric design, of algorithmic design, or generative design. And computational design in itself essentially means to use the technology of software engineering, or to use or to apply computational power of a system or of a processor, and use that to inform a design or a design process. So traditionally, like I said, most of our decisions are based on intuition or experience, or some books that we've referred to, or some projects we've seen. So all of them are more or less estimated, and there's no precise way to know its influence on our designs. What computation offers is a way to calculate this data and allow your designs to be informed by this data that you've collected from the site, or you've collected from a research that has already been conducted. So how can you use real numbers to come up with real analysis is where the computation design helps us. So as an individual, we might have a constraint of time, and we probably are able to only process 3 options, 4 options, 5 options, but computation helps us kind of bridge that limitation of time and human effort, and help and use the help of computers to kind of automate our designs. Parametric design, on the other hand, is an approach which talks about breaking down of a design in its parameters. So to kind of understand it super simply with basic example is, for example, I ask you to make a square. So the first question you'll ask me is, what is the side of the square? So any geometry in this world can be broken down into 2 segments. One is its rules or its algorithm, and 2 are its parameters. So when we talk about a geometry like square, its rule is a four-sided polygon with equal sides, and a closed polygon with 90 degrees between each side. So that is the formula. So when back in maths, physics, when we used formula to derive dimensions, it's the same thing. So when we talk about rules, it is this relationship between different aspects of a geometry, between lines. So if I'm to say make a square, you'd say what is the side? So the side becomes the parameter. So the parameter differentiates one square from another. So a square with say side 4 would look different than a square with side 10. So whatever variable or the change that we see between 2 squares becomes a parameter, but this logic of closed four-sided polygon with each side is equal and at 90 degree to each other becomes our algorithm or becomes our rule. So here you can see an example of this building, and on the right you can see it being scripted in Grasshopper, and on the left you can visualize the form of the building, and here we can see the person is changing the parameter. So it's basically changing the rotation angle of the building, and every time the angle changes from 0 to 1 to 30 to 40 to 60, we see its effect on the form. So whenever one parameter changes, it has an effect on the entire form. So when you have the entire code in place, as and when you start changing the parameters, you can see a reflection of it on the final form of the building or the geometry that you're trying to achieve. So this is how parametric design works. It is breaking down the entire geometry into variables or parameters and rules or algorithms. When we look at algorithmic design, it kind of falls into the major or the larger umbrella of computation design, but this focuses more on the relationship between elements of a geometry. So for example, here you can see that I have this apartment, and as and when the boundary condition or the periphery of this design changes, the relationship between the elements within that boundary changes. So, when for example, when my apartment is say 30 meters square or 40 meters square, I have a smaller dining table, I have a three-seater sofa, I have just one, single bed in the room. But as and when the size changes, goes on to 30, goes into 90, goes into 100, the distances between these elements change, and the size of these elements also change. So this is an example where one designer has kind of coded or broken down the entire design process into algorithms, and as and when we change the boundary or change the parameters of the boundary. So when we change the length and width of the rectangle, of the bounding rectangle, we can directly see its effect on the elements inside. So this is what kind of algorithmic design approach is like. And lastly, we have generative design. So generative design is where we really start tapping into the kind of possibilities that computation can offer. So really tapping into the power of technology, where they're using something like evolutionary techniques. So evolutionary techniques are basically what nature, like it's in close relation. The methodology is in close relation to nature. So we all know of this entire phenomenon of evolution, where nature creates, where nature has a design. By design, I mean human is a design, or butterfly is a design. So you have one design. So nature has created this design, and with every new generation, it creates some variation or some mutation between these offsprings, right? So every person is a little different from the other, but in essence, it's still a person. And when all of these are kind of brought into the world, they kind of compete with each other, and the one who is fittest survives. So that's what we know of evolution in nature. And here, computation is kind of allowing us to use the same principles. So what it does is that we have this script or this algorithm in place, and it gives us multiple iterations or multiple offsprings. Like in nature, it gives us so many, like tens, hundreds, and thousands of designs by changing different parameters. And once we have so many design options, we have hundreds and thousands of design options, it kind of assesses for us which of these 1,000 designs are fittest, which are, which are most efficient, which are most optimum, so they get to survive or they get to be taken forward in a design process. So what we can see here, for example, is this building complex, and this designer has used generative designing tools to create thousands and hundreds of variation of this building complex. And for him, the fitness criteria are, say, for example, light, shadow, and visibility. So whatever yellow portion that you see is the amount of light that or sunlight that the building receives, and the blue portion is whatever shadow that this particular form is casting. The lines that you see going around represent the visual field. So they show that when I'm inside the building and when I look at water, how many views I have towards the harbor area. So for this designer, say sunlight, shadow, and view were the fitness criteria or were its reasons to develop this design. So instead of two options or three options, I mean, every time, for example, our teachers or a client asks us to get more options, we are probably able to say make three options, five options, 10 options, at the max 30 options. But so there's a limitation. And that is where computation design or generative design steps in and says, let me make those generations and let me evaluate how good or bad they are. And, once I evaluate that for you, you can decide how to kind of orient your design process. So that is how generative design can play a really important role in making our designs faster and making them more effective in nature. Furthermore, if you're to look at the domain, which is to say, in a sense, the scale of this methodology, it's essentially scaleless in nature, as in, you could design systems from, say, furniture, from interior elements, from partitions, from ceilings, any element within interior design to, of course, the form of a building or spatial organization, what we call as the when we start with bubble diagrams and when we say what space will be next to what. So when we do a spatial planning of a system or of a building, that's also something that these methods can help you with, and all the way to urban design. So today, there are buildings and their entire sectors or entire cities or that are designed with these methods. So it's so as to say that this is not really specific to a particular scale of building, but it's just a different approach to design. So today, for that matter, even jewelry is being designed by parametricism or by computational methods. And here we have some examples of the domain that relates to us as architects or interior designs. We have a chair that's used for noise systems, or we have a parametric facade in place. And we also have urban scale where the networks are laid out according to the system, or the shape of the buildings are informed by a parametric design method. Further on, let's look at different tools and methods that one can use to generate such designs. So starting with Rhinoceros. Rhinoceros is basically 3D modeling software. So it's much similar to your, say, SketchUp or your ArchiCAD or Revit for that matter, where it basically looks at constructing a geometry, and it's pretty much manual in nature. So, we are all familiar with this workflow where, for example, if I were to make a box, I would start with, say, points, I would join them, or probably I'll start with lines and make a surface with that line, for example, shown here. And this is how this is how a normal workflow will take place. And if I were to make a volume, I'll probably just extrude this and make a box. So this is the kind of workflow that we normally are used to for all our softwares. And whenever we want to make a new box or we want to change the dimensions of this box, we have to kind of start from scratch. So we have to move this box, we have to start with another surface, and we have to kind of make a geometry with these parameters, but from scratch. So it is very difficult to kind of modify the existing geometry. And the approach is pretty much manual in nature. So when I shift a point, the entire geometry is gone and I need to start from scratch. So this is the kind of workflow that we're used to. But Grasshopper is where the scripting comes into play. So it's essentially making a software of your design. So what does any software do? So you give it some inputs, it will process the data for you, and it will give you an outcome. So that is what programming languages do. So Grasshopper is essentially a visual programming language. So you don't need to sit down and say learn C++ or Java and start typing and start coding for hours and hours like a software engineer. But so these people have made it easier for us, and they've designed these blocks, and they've designed this plugin which kind of visually helps us to code any kind of geometry we want. So here, if you see, there's a shift in our workflow. So we have the same 4 points. So for example, I have these 4 points in Rhino, and I want to bring it to Grasshopper. So I'll probably start. So on the right, when I have this box which says corner A, B, C, that's basically a component to make a surface. So to make a surface, I will need 4 inputs, which are different points. So here I'm trying to assign points from Rhino, and I'm trying to relate them to Grasshopper. And yeah, so here once I have the point and I connect it to my component, it generates a surface for me. It automatically generates a surface for me. And then I say I want to extrude it. So I use a component called extrude, and I use this base plane, and I say I want to extrude it in Z direction. And I want to say, for example, extrude it by 34 units or say 17 units. So what you see here is, as in when I change this parameter, this essential parameter of height, the box changes. Or when I change the location of the point, automatically the entire design or the shape changes. So this is to say that there is this crucial shift between how we model or how we approach. So Rhino, SketchUp, ArchiCAD, all of these are geometry based modeling tools where you have to physically or manually make geometries. But Grasshopper is the shift from geometry to logic, where you code a logic, and that logic in turns makes the geometry for you. So this allows us to make super flexible designs. So when you want to make that same design, you don't need to start from scratch. You can simply change its dimension and see what its effects are on the final form. Like you saw for that example of a building that we saw with the parametric design. So this is the crucial shift in the workflow, and these are the softwares that we'll be using during our workshop. Further on, we could also look at different methodologies. So those were the tools, but what are the methods? So here, this is an example of a brick wall that we designed. And on the left, you can see that we've scripted the entire design. And as and when I change the curves that it has to form, when I change it in Grasshopper, I can immediately see a change in Rhino, and those waves keep shifting. Or when, for example, I reduce the curvature, I could reduce the number of curves, could increase them. So I'm changing those parameters. I could also change the length of the wall or change the spaces between those walls. So all of these aspects become my parameters, and when I change them, I can see the result in my final design. So we started off by scripting the design in Grasshopper and seeing its kind of visualization in Rhino. And in the center, you can see the final form of the design that we came up with. So we decided this is the kind of wall we want to make, and this is what the final 3D looks like. On the extreme right, you can see a set of construction drawings. So since this is not a traditional wall where all the courses are repeated, every single course is has different relationships. So we made these construction drawings where each course has been numbered, or dimensions are given to it with reference to the previous course. So this is again something. So the design process is something similar to what we are used to in traditional methods. So we model it, we kind of come with the final form, and then we make construction drawings for it. In the next step, we moved on to execution. So we had conducted this workshop with students at Anant University in Ahmedabad, and on the top you can see students are starting with laying the foundation, and then they're being informed by those course-wise construction drawings, and then making every single course and shifting bricks in and out to kind of achieve the final form. And in the end, or in the bottom, you can see what that final uh, form turned out to be. So this was the kind of design that we could achieve. So here the workflow is pretty much, in terms of design, it's computational, but the execution is pretty much manual in nature or pretty much conventional in nature. The next example is of kinetic facade. So, we've seen these famous buildings by, say, Heatherwick, where he used those flutes which are going around, and kinetics or kinetic architecture or kind of design is another field that is coming up, and a lot of designers are experimenting with it. So this is basically the design process of kinetic facade that we made at CEPT. And this kind of is a flow chart. On the left that you see is kind of a flow chart. So we started off with different geometries of, say, square grid, or for tri-grid, or a triangular grid, or an undriven grid, and then we tried, that was a structure, and then we tried to see what different surfaces we can add on to this particular structure. So we tried triangular, we tried square, we tried angles, we tried to see what should be the angles between these surfaces or this structure. And in the middle, you can see different iterations. So iterations are basically offsprings of nature. So these are different outcomes of the same design. So, they have different angles, or they have different widths of the surface. In the middle, you can see we're looking at the modules per floor. So we're trying to look at how each module will be in relation to the next. So together, they can form a larger system. And the scale of it also. So will there be one module across one floor, or what will be the size of it? So will there be two, will there be four? So what will be the relationship of the size of a module to the size of a building? And in the end, we're also looking at how it will be attached to the structural system of the building. And of course, on the right, you can see GIF, which kind of simulates the movement of the facade. So this was largely the kind of design process. And the GIF that you see on extreme right was kind of coded in Grasshopper, and it's an animation exported from Rhino. And here we can see the entire process of prototyping. So like you can see, we tried different kind of modules. We saw how its movements are conducted. We made these prototypes using technologies like laser cutting, and we also looked at integrating motor and how switches can bring about that movement. We also programmed motors to give us this particular movement, or this kind of movement that we want. And here you can see we're trying to control the radiation, because this entire facade was kind of to control how much views you have and to block sun without having, depending on the movement of sun. And this particular part is where we actually got on to the execution of this facade. And here we're using laser cutting machines to make joineries, metal joineries, and then we're using manual methods to fold them, to assemble them. And we did all of this at the workshop. And once we had these joineries in place, we made this frame structure, and we attached motors to it and saw how the movement is conducted. And towards the end, we started putting on the framework, and then we attached the surface onto it. And this is the kind of movement that it allows. So of course, the entire facade was connected to a motor, and that motor was sensor driven. So as soon as you come close to this facade, it will start operating on its own. So this is the kind of facade that we prototyped and executed. And here the process is a little different. So the designing was completely computational in nature, and scripting was all done through Grasshopper and Rhino. And the prototyping was done using digital tools like all these laser and CNC and all these technologies that we have. And the final execution was a combination of manual techniques and digital tools. So it kind of followed the same process, but the tools and the technology used was a little different. Okay, so Yeah, so let's look at the scope and pedagogy. So by scope, I mean what all can you achieve through through this system. So we looked at tools, looked at methods, but what all can this system do? So in terms of scope, the first particular thing that's very evident from this entire discussion is parameterization, which is basically automating your design. So when you say that, when we talked about that surface or when we talked about that building, you're basically able to automate your entire design process, and just by the change of parameter, be able to change or see the change in the final outcome. So parameterization or automation of design is, of course, the first important advantage, if you say, of the system. On the other hand, it can also help you analyze your designs. So by analysis, I mean, for example, structure stability. So you've designed, for example, this entire curvilinear kind of a structure, but you also need to know if that is going to stand. So you need to know how to test its stability. So these softwares or these tools also help you evaluate if if it will take the load, if it will bend at certain positions. It can also help you evaluate if they're environmentally suitable. So for example, we saw that building where sunlight is controlled, or the effect of sunlight and daylight and shadow, all of this is kind of tested on the building. So you can know how much, if you have a window of say 3 by 4, how much of daylight will be coming in, or how much wind will that kind of an opening allow. So it helps you analyze your designs, not just helps you develop these designs, but also evaluate and analyze them and see if they're actually able to achieve the kind of outcome you want. And here we have the example of a viewful analysis. So when we talk about visibility, so you can see that there is this architectural envelope, and the dot represents a person moving around in that space, and the purple section or the area kind of tells us what he can see. So if he moves his head from right to left, what all can he see when he's moving around that space? And all the areas that are left in white are occlusivity, or are the areas that he cannot see. So such kind of analysis can be of great value to inform your designs. For example, if I'm making a retail store, it's the entire idea of retail store is, whenever somebody can establish a visual connection between the customer and the product, there are more chances for that product to be sold, right? So such kind of analysis can really help you come up with shapes, or can come up with shelving system that can allow for larger visibility. So what forms or what shapes can help you with that? And it could also be crucial in projects like museum design. So it's museums are our favorite thesis project. So it can also be of value. Where should the art be placed, or how it should be placed, what should be the angle, what should be the location. So all of these things you can actually test with real-time data and validate if what you've designed is actually working. So these are some things that this process can allow us to generate. It can also allow us to make different forms. So like we discussed earlier, similarly here you can see an example where there's this facade and it's covered by folded plates. So it's a folded plate structure, and the analysis of solar radiation is being conducted on each design. So these are different iterations or different outcomes, and the yellow portion shows a maximum amount of solar radiation that it receives, and the purple part shows the least amount of solar radiation achieved. So with every shape, it is making these analysis, and it is telling us, or it is informing us, that what should be the shape of these panels. So what should be its width? What should be the angle between them? What should it be trapezoidal in nature, or should it be shifted a little? So all these minute fine tuning of your forms that you're kind of envisioning or imagining can be assessed or can be analyzed, and you could come up with a final form which is maybe say structurally stable, or maybe is allowing the right kind of light to come in, or is able to give you the right kind of views, or whatever your criteria are. So you can actually test it and come up with different forms through this process. And further on, rationalization. So when I talk about rationalization, it basically means that when we model something, or when we design something in a software, uh, it is a continuous surface. But for example, I have this curvilinear arch going across a building, which is the roof of the building. So I have modeled that in a software, but it actually needs to be executed. So for it to be executed, we know that you cannot probably make a continuous system. So probably you'll have to break your design down into small pieces. So maybe you will have to get panels of that shape, or you'll have to cast concrete in that curvature. So rationalization is basically turning whatever you've imagined as a form or a design into something that can be actually constructed. So breaking that down in the form of material available, or in the form of technology that is available to construct it, and at the same time to make sure that it is viable. I mean, the production of it is viable. So by that I mean that, probably if you have this entire huge curve going across the roof, if every single panel is of a different shape and size, it will no longer be viable. I mean, it is possible, but not viable, because it will take a large amount of time to be executed. It will require a lot of money to make every single customized panel and then assemble it. But for example, I was to say that I can break down the entire curvature roof into 4 types of panels. And when I join these panels with different configuration, I'm able to achieve that form. So that essentially is rationalization. So from say 100 panels, I only have to produce 4 panels and then assemble them in different orders. So the project suddenly becomes much more viable in terms of time, in terms of cost, and in terms of basic workflow or the kind of resources that it uses. So this process helps break down all these forms that we imagine, but to make them really viable in nature. Further, we of course talked about generative design. So, go beyond these 3, 4, 5, 10 forms. And here you can see an example where visual connections from the building complex are calculated towards the central space, which is basically a landscaped area. And, it is kind of evaluating what all offices in these complex would be able to see the garden in the center, or the common open space in the center, because that's also an important character or an important driver of design. We always want more views, and we want our designs to be outward looking, to retain connection with nature or with surroundings. So here it is kind of analyzing. So different configurations or iterations are analyzing, and they're telling us, that this particular complex probably has maximum views possible, and hence we're able to come up with an optimal solution. Apart from generative design, this process also helps us in topology optimization. So what topology optimization essentially means is, for example, we have beams, and of what little we have paid attention to in our structure classes, uh, yeah, believe me, I was a student, and structures were the most least favorite of my classes, like most of us. So in structures, we kind of analyze beams and columns and all our structural elements, and we know that beam goes through maximum deflection in the center, and the edges or the supports or the ends of the column are does not have so many forces acting on it and does not easily bend. But today, when we make buildings, the cross section of a beam is always the same. So it's if it's 1 feet deep at the edges, it's also 1 feet deep in the center. But when we look at structure and the forces acting on it, we realize that probably the center of the beam needs to be heavier, and probably the edges need to be lighter. And with when we change the when we make the beams thicker in the center, probably it will add more load in the center. So that will also need to be balanced across. So what topological optimization does is it removes material from the spaces that are not required. So for example, even in columns or in slabs or whatever element or whatever form or the shell that you're trying to construct, it tells you where there's extra material and it's not required, and where you can use the where there are more stresses building up, and that is the place which is going through more corrosion or maybe going through more which has more exposure to the exterior, and that is why it needs to be thicker or needs to be more robust, or there are more structural forces acting on it, and that is why the cross section needs to be different. So today, where we are really trying to look at sustainable designs, or we're trying to use our resources and the material that we have in a judicial way, this methodology or this possibility can make allow us to use our materials. It can of course reduce the cost, but at the same time make more informed use of the sources that are available. Of course, cost optimization. So at the academic level, we do not talk much about cost optimization, but as soon as we step out, budgets are always super important drivers, or very important aspects of design. So what's this process? So here you have an example where we have this building, and on the right, I'm trying to change the parameters. So I'm trying to change the length of the building. I'm trying to change the, width of the building. And in the bit, I'm sure, I mean, I guess you're not able to see read the text, but it is kind of evaluating, or it is giving me the outcome of how much concrete is used, or how much is the surface area. So when we want to optimize cost, it is very essential to know the quantities, right? So instead of sitting down and calculating the quantities used for every single design outcome, this automation of design can directly help you that as in when I, for example, increase one floor, this is the amount of extra concrete that I will need, and hence this is the increase in the budget. So there is a direct relationship between the form that you're kind of generating to the volume, to the cost, and to the material required to make it possible. Right, so this probably tells us what is the surface area of the building, and which essentially ties up to the idea that those that much amount of glass I will require, and probably that is the amount of heat that this building will capture. So maybe you can look at maybe using glass or parts of glass, and then using some other material at different facades. So this is to say that in the very beginning of your design process, you are able to estimate, or you're able to find out different factors related to execution, and are able to control costs. So maybe you can say that maybe I can increase the spaces between the columns, and based on that, the number of columns would decrease, and the number of concrete and the number of metal used would also decrease, which will bring down the cost and bring it within the budget of the client. So these are the kind of informed decisions that you could probably make. And when we talk about digital manufacturing and using, so we saw some examples of, say, laser cutting, of CNC milling, and all of these technology that we today probably use to make our models, or they're used to make jalis in real world, I mean in real projects. But 3D printing is this one technology that is gaining a lot of attention, and this particular method helps us design buildings and construct them using these technologies. So especially after COVID situation, digital manufacturing is a domain that's kind of expanding really fast. And we have, from buildings to pavilions to even food is something that is printed with these 3D printers today. So so as to say that we always have seen this lag between what is being taught and what is going on in the real world. But here you can have a chance of kind of jumping into what advancements are happening in technology world over, be it in terms of design or be it in terms of execution, and kind of really, incorporate them in your design process at this point in your, academic journey. So digital manufacturing is also something that these process support. Lastly, we'll just look at the pedagogy of such systems or such methods of learning, which is basically broken down into 4 levels. Where first we're looking at, first we'll start off with say, scripting and modeling, where we look at how to code your designs or how to script your designs using Rhino and Grasshopper, and we'll kind of briefly touch upon the theories related to these. Forms, these terminologies, and again the methods that we're using. So there'll be a brief kind of sessions on theory, and we'll kind of just touch upon the analysis aspect of your designs. So that will contain the first phase of learning or the first level of learning. And moving on to the second part, that will be about advanced scripting. So we start learning how to really make really super complex forms, and we have these various plugins or geometrical plugins that can help us rationalize them, or make these truss structures, or make these super fancy forms. So there'll be some improvisation or some more focus on scripting. We'll also look at more theories of this process, and we'll start exploring the analysis bit, where we can look at, for
Excuse
example,
me.
visibly. Sorry, yeah.
Ma'am, I'm actually not in your class and I just joined.
This is actually an orientation session. So, Harsh, would you like to take that up? I guess you can join. That should not be an issue.
Yeah, I hope it's not a problem. Like, I find this class really interesting and like there's a lot to grasp from it. So I hope it's not a problem if I'm in here.
Yeah. That's sure. This is basically kind of to introduce everyone to this field. So I have no issues as far as the college is okay with it.
Yeah, I'm actually an individual, so I do a bit of architectural stuff on my own. So that's about it. Yeah. You can
Okay,
carry on,
sure,
ma'am.
sure. Please join us. Okay, all right. So, yeah, so the second level talks about, kind of learning these advanced skills of scripting and exploring some plugins for more complex geometries. The third level would be about analytical tools. So, we talked about structure, we talked about environmental, we talked about view fields. We will also probably analyze circulation, because that plays a huge role in our designs, or spatial distribution of spaces. So all these various analytical tools that can help you evaluate the designs or the scripts that you've made. So in the third level or third module, we'll be looking more into the analysis of it. And of course, finally, we have the generative tools, where we'll be using algorithmic thinking and evolutionary techniques to generate these tens and thousand forms and evaluate and come up with what is best fit. So this is sort of a breakdown of the kind of workshop or our approach to teaching for this particular niche in design. And yeah, so that was the larger intent of the session, where we were trying to introduce to you to this field, and expose you to the potential that it offers and how it can fit into your academic curriculum. And we can design something as fascinating as the forms by Zaha, and it could be brought down to real local scale, where we could demonstrate through that brick wall or through that kind of facade, where given the technology that we have right now, it no more has to be something that exists as imagination. When we look at these renders, we think, oh wow, I don't know how they did it, I don't know if I can ever make those designs. But this is to tell you that it is very much within your reach, and it is very much something that you can explore. So after postmodernism and after deconstructivism, as leading movements in design and in architecture. Parametricism is something that was formalized by Patrick Schumacher, who's now heading Zaha Hadid Architects and who has been on team since day one. So this is a language that is now probably the most dominant language in our industry, and every single studio, small, big, established, or multinational institutes or design studios are kind of starting to approach. So it's not something that's just happening in the West or in foreign countries where they have better technology, but today people in Ahmedabad, in Anand, in Mumbai, in Delhi, in Hyderabad. So all of these places are doing it, and it feels a little far fetched, but it's very much here. And I it's a safe bet to say that if, say, not 2 years down the line, definitely 5 years down the line, it will become a part of our most preferred workflow. So today we already see a lot of firms shifting from CAD to BIM, shifting to Rhino, shifting to Revit. So they're already started incorporating these methods into their workflows and their design processes. So basically, the idea was to kind of introduce you to this possibility, and get you up speed with the next big transformation in the industry that we're heading towards. And yeah, I hope it was able to spark some interest, and I hope you could benefit from this kind of an session. So thank you for your patience and listening to me. Now I'll invite my colleague Parul, and she'll help us address the questions that we
Sure.
have.
Thank you very much, Drishti. It was really insightful,
Thank
and
you.
it actually did spark a lot of curiosity. And maybe since I'm, moderating, I can take the liberty of asking the first question if that is fine with you.
Absolutely, absolutely. So I
Yeah.
welcome Parul, and she'll help us, take these questions.
Sure. So my question is basically a two-part question. First is there are a lot many logistics as we saw in that kinetic facade system. There are a lot many logistics that goes into making of it to make it functional and operational. So my question is that how much of that logistics are to be designed and calculated by us, and how much is like suggested by the software or the any tool that we use.
Okay. Parul, would you like to take that?
Looking on the part where we kind of design it. So at the end of the day, we are the designers. Fine. So I won't say the computer would generate something for you. It is us generating. But having said that, yes, we keep on kind of the tools would only help you analyzing something. So at the end of the day, we were the designer. We were kind of making the changing. We were try and working hard to kind of make that thing work, and computers were kind of helping in stating whether the things we were making was optimum, or as she mentioned, the best possible outcome of the design we were uh, uh, design we were kind of looking forward to. So it goes hand in hand. I can't say ki everything computer had designed, and we cannot also state that it's us who's designing. It's us who's designing. So I would say that.
Yeah. So to add to that, so there's this major shift in the process where when we model, or today when we design, we are designing the product or the form. But what computation has to offer is the shift where we are designing the process which will design the product. So we're not designing the product directly. We're trying to put in place what the process should be to design that product. And we kind of, make that script or make those logical steps, and then the computer kind of evaluates and processes all that data and designs the outcome. So that is where the entire shift in thinking or approach happens. So it is not It's not something which we can initially imagine, oh, that this would be the final outcome. We can only focus on the process, and we can say that, the process has to be right, and that process will in turn give you a design which performs. So humans are kind of designing the process, and that design process will design the actual product. So that's the crucial shift. It's using the best of both, wherever humans have a limitation of, say, time, of resources, of number of people, or number of man hours. Computers can help you make those outcomes faster. But in the end, it is humans who are kind of is the designers who are making the final decision. So it's not dystopian in nature. It's not something that we see in sci-fi movies where the computers will take over and we'll have no control over it. So it's definitely not that. At least yet,
Just from a
it's not that.
Adding to that, also because so basically we are kind of designing the process that eventually governs the form. So if you saw the video, the initial
Should I go back to it? Yeah,
yeah. So can you play the video? So can
yeah.
you see the initial prototyping? We were dealing with materials also here. So even so, initial designing we started with material exploration. We were using bamboo sticks. I remember we were using paper. We were using textile also once. Then we came on to MDF. So do you see every material would have its limitations. So you would be kind of tested at every level while you experiment. So for today, if I tell you to sketch a pavilion or sketch a facade, so the conventional way the students do it, or we back in our time used to do it, we used to sketch it. But how do you sketch anything? You can always sketch or kind of design anything which you've seen somewhere. It is always something that is kind of coded in your mind. You've seen it on Google, or
real
maybe you
picture of
kind
it.
of you kind of amalgamate two things and kind of design something. But here we were kind of exploring from the sketch how the material behaves and how we can take that forward and kind of put computational design into place and then see how things work. So it's a to and fro process. You have to do hands on, then go back to digital working, then analysis, then hands on. So everything comes into play.
Okay, and maybe the second part of my question could be related to it. For example, if we are changing form, I mean through a parameter, let's say I want shading as per a particular climate condition, and I'm creating a bit modulation in the form to create more of the shadings. So does the tool allow us to like change the structures, the size of the structural system by itself, or then it has to be upgraded again by ourselves?
Drishti, are you taking this?
Yeah, so Harsh, so there are different ways. So when we looked at parametric design, or when we looked at algorithmic design, there we were manually changing the dimension, right? So if you are just coding a design, then those changes or those modifications will be required to be made manually. You'll have to manually change the spacing, or you'll probably have to change the length of the chaja, or probably the angle of the chaja. So you'll manually be changing those dimensions. But when we look at generative design, which I talked about, where we're actually tapping into the potential of a computer, so generative design is kind of a process where the computer itself will change all the dimensions and it will evaluate. For example, if I have a chaja and you say it's a rectangular chaja by, say, 2 meters by 4 meters in length, for example. Uh, so 2 meter and 4 meter are, it's a rectangular chaja, and those are my parameters. So when I do it manually, I will check, half a meter, 1 meter, 2 meter, 4 meter. So I will manually try to change the dimension and see what the effects are on the final analysis. But when I plug this entire software or entire code into a generative tool, the computer itself will make all these modifications. So it will generate one outcome with the chaja as 1 meter wide. It will generate another outcome with chaja as half a meter wide, and so on and so forth. So it will the computer itself will make those changes and give us these tens and hundreds of different permutations and combinations of the design that we have set across, and then help us evaluate कि अच्छा इसमें सबसे ज्यादा लाइट आती है या फिर इसमें सबसे कम लाइट आती है. So I am able to achieve what I set to through this design. So to answer your question, it depends on what tools you are using and how advanced your scripting technique is.
Okay. So just like final, not a question, but I'm just like curious about. So for example, if a form of building is getting changed, so we still need to know the like the capacity of its members, structural members, to take the load, or the software will itself intuitively guide us that this is the size of members that you need because the form of your building is getting changed. So would it happen that way?
Parul?
Yeah, so when you talk about generative design, so are you asking, will the software give you exact dimension and exact factors? Are you asking that?
Yeah, I mean, let's say if I change the building's profile, so maybe it help us to create a different structural system. So would it do it by itself, or then we have to again design the whole structural system?
No, it'll do it by. Okay, I'll just give you example. Drishti, can you go back to that grasshopper wala slide where you have the sliders?
Yeah.
Can you play and just yes, extrusion and the slider. Okay. Okay. Can you zoom in? Okay, fine. Pause kar de. Okay. So do you see the slider? So when we talk about generative, so this slider, for example, if we're talking about a structure, you're talking about dia. Let's assume we're talking about a dia of a structure. So I say this slider would would be an input for dia. Assume that. Fine. So while if you're using a generative plugin, it gives you a leverage of it will automatically connect to this slider and give it an optimum result. It will automatically state that okay, this is so you'll have to also give it a fitness criteria. So when we talk about fitness criteria, you would also have to say, okay, I need to you give an example. What do you need to maximize or minimize? Shade, you need maximum sunlight, whatever your criteria is, you will only state that. You will state, okay, I need maximum sunlight to be able to, or you can also give loads. So maximum load on a structure. So according to that, it will give you every possible outcome, and you could actually see what could be your dia for what load, what dia do you need. So it does everything.
Yeah, so to add to that, the third level of pedagogy where we talk about analyzing tools. So when you script a design, you've already made, for example, the form of the building. But after that, you will also have to incorporate these analysis tools. So within the script, you will have to ask for it to kind of conduct these analysis tools. So whenever you change the spacing between columns or whenever you change the size of the columns, it will automatically analyze the structural loads that are happening on that particular cross section, and it will show you a result that there's too much stress here, so probably you need to make it thicker, and there's less stress here. So it needs to be coded into your design, but it will do it automatically. You don't need to go ahead and do it every single time.
Okay. So
Yeah.
thanks for that. And I think we have a related question in the chat box.
Yeah.
One of our faculty, Pratik sir, is asking that does it allow optimization of material? I think you touched that part. Yeah, it removes material from the part where it is not playing an active role in structural load transfer.
Right.
Maybe you want to like quickly elaborate on that part.
Could you please state the question?
He was just asking that does it allow for optimization of materials?
Yeah. So here we looked at topology optimization. I think that is what he was probably asking about. Yeah.
Yes.
So yes, to answer the question, yes, it can allow for optimizing the materials that we use.
Okay. So we'll open this up to students. You may pitch in. Anyone who has a question.
There's a question in the chat box.
Yeah,
So
Harsh, could you, yeah, please read
Yeah,
the question because a lot of people, there could be a mess.
sure,
So
sure, not a problem.
please, everybody, please put your questions down in the chat and we'll take it one by one.
So I think, yeah, it's a very direct question that can you tell us about the workshop and how do we participate in that?
Okay. Um,
and
I,
he's asking when.
And when? Yes. So Abhishek,
I think
we all,
Harsh will have to
yeah,
answer
I
that
think we
question for
all can
us.
answer this. That the precise reason for conducting this workshop was to orient all of you for this field of knowledge. And since we feel that it has happened quite well now, we'll float the paperwork now and we'll start getting enrollment for the same. So maybe we'll just get a bit of a hint from Rishti and Parul, and then we'll float the paperwork to get the enrollment. So yeah, it's pretty much in pipeline. It will happen soon. And the next question is from Tanusha Ghosh. She is asking that in algorithmic approach of designing, is there any basic like formulation or ratio that you consider while designing? I mean, it could be a bit generic question, but I think what she's asking is what are the parameters that you consider before you start a designing of a building?
Parul, would you like to take that up?
I didn't get the question. Is she
Sorry.
asking?
So maybe if I just like,
There's,
yeah, I just
yeah.
put it in other
Uh,
words. For example, let's say if I as an architect is starting to design a building, so I want to make it climate responsive. I want to utilize as minimum material as possible. I want to make it like economical. The structural system has to be uh, occupying lesser footprint. So these are like certain parameters that I consider as an architect before starting a design. So how many of such parameters can the tools and software accommodate? I mean, acoustics, do they accommodate acoustics also, for example?
Okay, so
uh,
Drishti, you take the first part, I'll take the caustics one.
okay. So, to first answer the first part of the design, there is absolutely no limit to the number of parameters that the software can take. It is you as the designer, and it depends on your coding capacity or capabilities or skills, and it can be as many number of parameters that you can handle. And first question where she asked that what would be the parameters that I would consider. So that essentially depends on you. So that is where the human or the designer part comes in.
Okay.
So you start with a blank canvas and you say, for example, for me, the width of the chhaja is important. Like to go back to the example that you gave, so I will use the width of the chhaja as a parameter in my process of coding. So you as a designer are designing the system and you will tell the software that these are the factors that are important to me or these are the relationship between each other.
Okay. Okay.
So it's completely on you. It is your design senses and your understanding of the problem and your ability to convert that problem into a script. Yeah.
Okay. Okay. Sure. Sure.
And second part, Parul?
Adding a caustic thing, yes, you can actually analyze the sonic conditions inside any space or even in the on the urban context. So there is this firm in Germany called Arup Acoustics. They've kind of built a prototype that is responsive to the sonic conditions inside the room. So it depends upon the number of people occupying the room. So if the number of people are less, the ceiling kind of is kinetic to cater to the sonic conditions of the room. So it is responsive to acoustics. So yes, you can deal with acoustics also.
Okay. Okay.
Just to add a little bit to that, so the major big advantage of this system or of Grasshopper as a software or a plugin is that it is open source. By open source, I mean that at this very moment, there are hundreds of software designers out there who are making these different analytical tools, different components, and they're putting it up on internet. And you can simply download those plugins into your software. And for example, we are now dealing with pandemic design, post-pandemic designs, where the entire distancing is into picture and the movement of people is into picture. So like in real time right now there are designers, coders, software engineers who've developed these different tools or plugins that probably you can for a public space You can evaluate how much distance there will be, or what will be the movement, and will it be compliant to the COVID regulations. So just so to say that, what you can analyze, it is infinite. So, and it keeps on increasing. So what you require in your design is what you have to search for and kind of use into your scripting of Grasshopper.
Sure, sure. So that was comprehensive answer. I'll go to the next question by Krishna Dalal. She has a very very typical question that at which age, I mean, she is from third year, I guess. At which age should student be exposed to the knowledge of digital architecture? I mean, which part of their architecture curriculum?
So this was a big debate back in my universities also. So if we're talking about only parametric tools, I guess tools and softwares can be introduced from first year itself. But when we talk about introducing students to a parametrically oriented design studio, I would say third and fourth year are a much those students have a much better background of architecture by then, because we don't want a first year student to get over fascinated by parametric architecture and kind of forget the base and the main architecture that he or she should do. So I guess as a design studio it should be third or fourth year, but as to introduce the software it can be from the first year itself.
Okay, because I like there's this myth, if you want to talk about that, sometimes it's the thing is getting propagated that this parametric architecture is kind of killing your intuitive design approach or maybe creativity. So, and it's kind of making you handicapped, but we understand it's not that way. So maybe you want to like throw light upon that part.
Yeah. So so it is a debate that even today, I mean, since I started learning architecture, and even today, when I'm scripting, I start with pen and paper. I sit down and think, okay, what are the steps required? What is the design? So the shift is when we talk about, say, SketchUp. Often we hear that, because if you start from SketchUp, you kind of are bounded by its rectilinear lines, and what software can do kind of informs your design, right? So that is the skepticism that involves using technology. But here we're not talking about modeling at all. So modeling is an outcome of this design. What we're talking about essentially is the process of design, right? So I mean, I can start with a curve as much as I can start with a line, and I can explore curvilinear forms as much as I can explore rigid forms. So here the idea is not really to use it as a modeling tool, which SketchUp and ArchiCAD or all of those softwares or AutoCAD helps us. But here is the idea to break down your thinking process and your design process. So it is crucially driven by your idea as a designer, and it is not constrained by what the software can reproduce or what the software can visualize. So of course it is a combination of both, and how you understand a problem be of crucial will be a crucial factor in deciding your design process. So one, that it is both hand in hand, and two, that you are kind of designing it, you're designing the process. So you are taking all the decisions, and none of it is informed by the computer is only helping you make those decisions faster, or is able to help you evaluate that, you make this courtyard of 5 by 5, is it really helping, or is it too tight, or is it too big? So it is helping you be a little more informed about your designs, and at the same time it is helping you calculate many different options. So if I were to manually start sketching, I'll probably make 5, 6, 10 options, but computer can give you, say, 100 or 1,000. So it's ultimately how we use it. Like it's with any other technology, with Instagram or with Facebook or with any technology out there. It essentially lies, the onus of it lies in the wisdom of the designer and how that person chooses to use it, right?
True, true, very true.
Yeah.
So yeah, maybe I can invite now Vijay sir to ask his question.
Hello, Drashti.
Yeah. Yeah.
Rather than say a question, I just want to know. I'm just a little bit curious about this all thing, the process which you have done. So we all know about that. Every tool or every process or any software has certain limitation. So I just want to know
Right.
okay, whatever you process which you have discussed or explained. I just want to know what are the limitations which you have found during this
Okay.
process in terms of material, in terms of structure, or in terms of any other thing. I just want to know that thing as a designer. What kind of limitation which you have found it out during the process?
Okay.
Yeah.
Okay. Super. Amazing question. So, um, every designer or every computational designer kind of has to deal with this idea of qualitative to quantitative. By which I mean that today when we design, we always think of space in terms of its quality. For example, a cafe or a room once should be cozy. A monument has to be, for example, imposing in nature. It should have this kind of a volume. So we always define our spaces in terms of the quality, right? Even when we talk about sections or when we talk about museums. So as designers, we always think of a quality of a space as the important factor in our design. But computer does not understand the word cozy, right? It does not understand the word spacious. So the challenge here is to be able to convert the qualitative aspects into quantitative aspects that the computer can understand. So it only understands zeros and ones and digits and data. So how do you convert that particular quality into a quality or into a quantity that the computer can understand and respond comprehensively? So for example, here we have this analysis tool. Yeah, here. So we are talking about view field and the compactness. So the fourth factor, which is compactness, it kind of directly relates to the spaciousness of a space. So, the more compact, so the lower the number is, the more compact the space is, and the higher the number is, the larger the space is. So when I want to make a spacious or a large spread out kind of a structure, I will try to maximize the compactness. I mean, I would try to, make the system less compact. And for example, if I'm designing a bedroom or a cafe, which needs to be, more in relation with the human scale, I will try to increase the value of compactness. I'm sorry, there's a lot of disturbance. Could we all be on mute? Yeah, thank you. So here, this is an example of how quality of a space can be quantified and understood by the computer, and it can give you a decisive value. So when we design our buildings, we start with quality and we also end with a quality. I mean, the outcome is also quality. So when I say I want to control the amount of sunlight getting into a room, what I'm essentially saying is that I want the environment of a room to be comfortable. So comfortable again is a quality, and it needs to be broken down into what computer can understand and analyze. So for example, a comfortable space can be 23-degree in temperature, or it can have a particular speed of wind, or it can have a particular ventilation, or it has to be a certain size. So what is the comfortable space needs to be broken down into data and the kind of language the computer understands. The advantage, so this is a drawback, but its advantage is that you can really evaluate and show as a proof. So it is very scientific in nature. Keep going back to the example of a courtyard. So when I make a courtyard of 5 by 5, I don't really know if it is able to achieve the intention that I have as a designer. But if you're able to code it and if you're able to convert it into a language that the computer can understand, it will show you, okay, so because of the presence of this courtyard, the temperature in the surrounding areas has dropped from 30 degrees Celsius to 22 degrees Celsius. And that falls within the comfortable range, and hence my design is a success. So I can with proof say that what I've designed is actually performing in the way I want it to be, and not something which is very intuitive and very estimation oriented. Right? I hope that answers the question.
Sure, sure. And I think that line could be taken as the punchline for today to convert the qualitative aspect into quantitative. It really explains a lot about the whole process. And yeah,
Yeah,
we will take the last two questions. One is from Nana and one is again from our faculty. I think they seem equally excited as our students. So I
super.
think yeah, I'll club both of the question. I think
Okay.
Azhar sir may be invited to ask question directly. Sir, would you want to ask directly?
Yeah, it's related to Vijay's questions and what you explained. Like, I'm curious, is it all in Grasshopper and in such attachments? Because like, I attended one of the workshops where I found like for analyzing daylight is different software, and then with daylight, if you want to check the heat, as you said, the example of courtyard, right? So we want to check that the heat gain and thermal comfort range according to the sun path. Then you have to again take your model or whatever process you are designing and the scripting to another extension or maybe another software. Then for wind is different software. So what in terms of parametric design, what you have shown, it's very
Hmm.
great to see the example as you quoted the courtyard. Maybe
Hmm.
we can see the same time the light quality, even the wind and the daylight factor and the comfort and the temperature both. So is it all combined when we make a model and a design and scripting, or then here also what you are means in terms of workshop what you are teaching or showing, is it all in different softwares again? Because I know some of the tools like Rhino and Diva extension, and then there is Dr. Andrew Maas tools also. Some of the tools
Right.
you have mentioned in the references. So is it
Right.
still shipping, or we can see a building together at once with all the parameters and generate
Okay.
analytical analysis sheets?
Okay. Okay. Parul,
Yeah, so for if you are purely talking about Grasshopper, you do have extended plugins for Grasshopper. So you would not require to take your model and kind of export it to different software. So for example, you are Grasshopper and you're only dealing with light, acoustic, and shade, for example. So you have extended plugins within Grasshopper that you need to kind of install, and you can at the same time change your script, maybe it's little change in your script if you want to see acoustics, and those changes can be seen on your Rhino screen. And adding to that, you can do and you do have analysis plugins for Rhino also. So it's not only Grasshopper that can do the analysis, you can also do analysis on Rhino itself. So like Grasshopper is an extended plugin for Rhino. You do have other plugins for Rhino that can do your analysis. But having said that, they would not be generative like we have it in Grasshopper. So once you've done one analysis, you have a result. So if you need to change something, you would have a different result. While in Grasshopper, you can actually see what change can lead to what change in form, or maybe your factor that you're governing. Is that
yeah, yeah. Just to add to that, Rhino Grasshopper. So Rhino is compatible with almost every other software. So if at all there is some specific task that you want to perform with some other software, you can absolutely export the files. But since, like I mentioned, it's an open source platform, so anything that we can imagine, people have already coded and made plugins for it. All these software engineers in the world have already made millions and millions of plugins that can help you evaluate any possible thing that you can think of, so also it's a growing community, so with changes in time there are more plugins coming up. So all the basic analysis that we need are already present, and it is still an expanding community. So yeah, for you would essentially not require to juggle between many different softwares to evaluate your designs. Yeah.
Sure, sure. So, yes, I think we can conclude the session. And on this note, I would like to invite our professor Kandav Rahul, sorry, for the vote of
Okay,
Okay.
uh, okay. Our guest speakers, Dusty Kaura, Parul Chauhan, respected faculties, my dear students and participants. Good afternoon all. My name is Kandar
Afternoon.
Tawal. I am a HOD of Interior Design Department at APID. I deem it a great honor to propose the vote of thanks to all who have helped us in making this webinar such a great success. I would like to thank distinguished speaker Drashti and Parul for making excellent and interesting presentation on parametric design approach and expose us to the scope with the relevance of the same. I also wish to express my vote of thanks to our Transcending Thursday team and IT team for providing encouragement and support for this event to be a successful one, as no program can be successful without team effort. So I extended my big thanks to our APID family team for this support and all our volunteers. Thank you guys for making this event successful with your contributions. Looking forward to have many such interactions and interesting topics we can discuss. Thank you all. Another important announcement, please fill the feedback cum certification form, which is already shared in your chat box. Okay. See you on next Transcending Thursday event. Have a nice day. See you again.
Thank you,
Thank you.
Drishti. Thank you,
Thank you so
Parul.
much, Harsh. Thank you so much, Mr.
And
Kandor.
we'll very soon float the paperwork being in contact with you. So we'll just get back to that, okay?
All right. Thank you so
Sure,
much.
sure. So thank you both for joining. Thank you again. Thanks.
Yeah.